Hello and welcome to the first lecture for Unit 3 of Intro to Logic. In this unit, we're going to be learning an entirely new logical language called predicate logic that builds upon the logic we were learning before, which is called sentential logic. Let's first talk about some of the limitations of sentential logic. So in sentential logic, we use an uppercase letter to stand for an entire statement. Like we might use the letter K to mean Kanye West is an egotist. Because we have a single letter representing the entire statement, we can't represent what that statement has in common with other statements. So consider Kanye West as an egotist. That has something in common with Kanye West as a musician. It has the same subject. It also has something in common with Lindsay Lohan as an egotist. It has the same predicate, even though it's a different subject. There are also statements like everyone is an egotist or someone is an egotist that also has the same predicate in common with Kanye West as an egotist. Now, because in sentential logic we use a single letter to represent the entire statement, we can't represent what that statement has in common with certain other statements. So if I say Kanye West is an egotist, therefore someone is an egotist, it seems like that's a valid argument. It has the form, this person has this property, therefore someone has this property, which seems like a valid argument. But if I represent that in sentential logic with K, therefore S, and I do a truth table for that, obviously it's not going to come out as valid. So what we want to do is we want to introduce a new logical language that actually represents parts of statements and what they have in common. So in predicate logic, we have different kinds of symbols for subjects and predicates. So we're going to use lowercase letters except X, Y, and Z to represent what we call subjects. Now, subject-predicate distinction is usually something you use in grammar, but in logic, we understand subjects and predicates a little bit different. So in logic, a subject is a specific individual person, place, or thing. Now, when you hear person, place, or thing, you think noun, but we actually don't use this for all nouns. We only use it for names of specific individual persons, places, or things, and we use lowercase letters. So Amsterdam, we might use the lowercase letter A. For Kevin, we might use the lowercase letter K. For Britney Spears, the lowercase letter B. For the Pope, we might use the lowercase letter P. For the number 5, which is a specific number, we use lowercase letter F. Notice that Amsterdam is a specific city. It's not just cities in general. Kevin is a specific person. Britney is a specific person. The Pope is a specific person, so we use lowercase letters for them. We're not going to use lowercase letters for a word like city, since the word city is not a name of a specific city. Now we use uppercase letters in predicate logic for things we say about subjects. These are our predicates. You can think of a predicate as having a place to fill in with the subject. So blank is hungry is a predicate. We use uppercase letter H for being hungry, uppercase letter T for playing tennis, uppercase letter D for driving drunk, uppercase letter P for a number being prime, uppercase letter L for someone loving someone else. These are things we say about subjects. We call those predicates. So what we do in predicate logic is we put these together to form statements, and we put the capital letters first. So if I want to say Kevin is hungry, I would write HK. You put the H first, uppercase H for being hungry, lowercase k for Kevin. If I want to say Britney Spears is hungry, I can use the same predicate, again, uppercase H, followed by a lowercase b. If I want to say something else about Britney, I'd still use the lowercase b, but I use a different uppercase letter. So I might write TB to mean Britney plays tennis. If I want to say 5 is prime, uppercase P for being prime, lowercase f for 5. Now, some things that we say about subjects, we actually say about more than one logical subject. If I say the Pope loves Britney Spears, now grammatically the Pope is the subject, but logically we're considering this to be about both the Pope and Britney Spears. So logically we're just going to use the letter L for love, and we're going to follow up L with 2 lowercase letters. So write L lowercase p lowercase b to mean the Pope loves Britney Spears. Those are called polyadic predicates, and they contrast with monadic predicates. Monadic predicates are predicates that just apply to one thing. Polyadic predicates apply to more than one thing. And we use a polyadic predicate, the order of them usually matters. So if I say Kanye loves Beyonce, I might use uppercase L, lowercase k, lowercase b. And you see the order matters because that means Kanye loves Beyonce. If I want to say Beyonce loves Kanye, I'd still start with the uppercase L for the predicate, but then I'd follow it up with a B and then a K to say Beyonce loves Kanye. Now, strictly speaking, we get predicates that apply to any number of things. In this class, we're usually going to focus on things that either apply to one thing or apply to two things, but you could have a predicate that applies to three things, like between for numbers. Blank is between blank and blank is about three things. 7 is between 5 and 9 is between three numbers. 7, 5, and 9. So uppercase B for between, then lowercase s, lowercase f, lowercase n, means 7 is between 5 and 9. We're not going to focus too much on predicates that apply to more than two things in this class, though. We saw in our first unit that, well, I should say we're going to use the same symbols, the and symbol, the or symbol, the not symbol, the arrow symbol to mean the same thing we used them for before. We'll put them before these new statements to form new statements. We saw in our first unit that when you use the word and between two names, sometimes you can translate that where you use the and symbol between two whole statements. So if I say Chandler and Monica are hungry, that means the same thing as Chandler is hungry and Monica is hungry. So that's still the same way you would translate it now, only to say Chandler is hungry, you'd write HC, hungry Chandler, and HM, Monica is hungry. But sometimes when you have the word and between names, it actually isn't something you can break up into two thoughts, one about the one person, another about the other person. So if I say Chandler and Monica are engaged, that probably doesn't mean Chandler is engaged and Monica is engaged. It probably means they're engaged to each other. If they're engaged to each other, that's like love. It's a relationship between them. So when you have a relationship between two things, you're going to use a polyadic predicate. So I would translate this as ECM, Chandler is engaged to Monica. That's a polyadic predicate. It's a relationship between two individuals, Chandler and Monica. We represent that relationship with the uppercase letter E. So again, we're going to use the wedge to mean or, the arrow to mean if then, the two-way arrow to mean if and only if, ampersand to mean and, not to mean not, just like we did before. So say Peter is a Republican only if he is ignorant. We're going to represent that with the arrow. Write RP to mean Peter is a Republican. Arrow, now the he and he is ignorant is Peter. So we're not going to write this as IH, we're going to write it as IP. So RP, arrow IP, Peter is a Republican, arrow IP, Peter is ignorant. Unless Peter plays tennis, then Allison loves him only if he does not drive drunk. Unless is if not. So if it's not true that Peter plays tennis, if not TP, then, that's the arrow. In parentheses, Allison loves him. That's Allison loves Peter, LAP, arrow, Peter does not drive drunk, not DP. So not TP for unless Peter plays tennis. Arrow, Allison loves him, LAP, that's Allison loves Peter, only if it's not true that Peter drives drunk, not DP. If neither Ross nor Phoebe are hungry, then Monica will not cook. So neither Ross nor Phoebe are hungry is, it's not true that Ross is hungry and it's not true that Phoebe is hungry. If that's true, if not HR and not HP, then it's not true that CM, right? It's not true that Ross is hungry and it's not true that Phoebe is hungry, then Monica will not cook, not CM. You can also do neither nor with a negation outside of an or statement. Then it looks like this. If it's not true that either Ross is hungry or Phoebe is hungry, then Monica will not cook, not CM. If you have a word like unkind or impolite, that un or that im, that prefix, really means the same thing as a not. So we can treat Allison is unkind as not KA, if and only if it's a two-way arrow. Peter is impolite, not PP. So PP means Peter is polite. The not turns it into impolite. So it's not true that Allison is kind, if and only if it's not true that Peter is polite. Now, if that's all there was to predicate logic, it wouldn't really be that different from sentential logic. We would just use multiple letters to represent statements. What really makes predicate logic interesting is when you introduce quantifiers. So quantifiers are things you use when you want to talk about not specific individuals, but all or some members of some group. So we don't always say Kevin flosses, we might say all dentists floss. So we're not talking about any specific dentist, we're talking about all of them. Say some politicians are alcoholics. We're not saying which politician we're talking about. It's not a specific individual. Everyone loves Bjork. We're talking about everyone there is. Now, Bjork is a specific individual, but the everyone here isn't a specific individual. So we can use quantifiers with them, and in predicate logic, quantifiers go along with variables. So lowercase letters at the beginning of the alphabet stand for specific individual subjects. But we use letters at the end of the alphabet as variables. Now, variables don't stand for specific things, but they replace words for specific things. So if I write HK to mean Kevin is hungry, that's about a specific person. But if I replace the K in HK with an X and get HX, that means something like it is hungry, where we don't know what it is. By itself, HX is neither true nor false. It's ambiguous. We're not saying what we're talking about. So we can remove that ambiguity by prefixing the statement form with something we call a quantifier. Now, there are two quantifiers in predicate logic. There's an upside down A called the universal quantifier, and we put it with a variable, and it means for every value of the variable, what we're about to say is true. The other quantifier is called the existential quantifier, which we write with a backwards E. And that means for at least one value of the variable, what we're about to say is true. So if I write backwards EX, HX, remember HX by itself means X is hungry, where we don't know what X is. If I put the backwards EX, it means for at least one value of X, there's at least one thing I can interpret X as being, where HX is true. So for at least one value of X, X is hungry. So that basically means something is hungry. For upside down AX, BX, where BX means X is beautiful, by itself, X is beautiful is neither true nor false, but if I say upside down AX, BX, that means for every value of the variable X, what I'm about to say is true, so X is beautiful. So whatever I interpret X as being, everything is beautiful. So you can think of upside down AX, BX as standing for a list of things. BA, Amherst is beautiful. BB, Brittany is beautiful. BC, Chicago is beautiful. BD, Detroit is beautiful. That A, B, C, D, E, F, those are all possible values of X. Just like if I were to write X plus Y is Z in algebra, 1, 2, 3, 4, 5 are all possible values of X, right? So if I write BX, there are different values that X can take. But if I say upside down AX, BX, I'm saying that every value of the variable makes the statement true. So Amherst is beautiful, Brittany is beautiful, Chicago is beautiful, all of those. And that list would go on forever. I'd list everything there is in the world, and I say it's beautiful. Each one of those is a possible meaning of BX, right? If all of those are true, then upside down AX, BX is true. But if I write it with the backwards E instead, if I write backwards EX, BX, I'm saying for at least one value of X, BX is true. That doesn't mean all of these are true. Maybe Amherst is beautiful, but Brittany isn't, and Chicago isn't, and Detroit isn't, right? So backwards EX, BX only requires one of them to be true. So long as they're not all false. If they were all false, backwards EX, BX would be false. But if even one of them is true, then backwards EX, BX is true. So backwards EX, BX means something is beautiful. Okay. Now, normally we don't talk about absolutely everything. We talk about every member of some group, right? So we're going to understand these by using the quantifier applied to a statement form that has a conditional in it. There's an arrow. So I say all frogs are green, every frog is green, any frog is green, each frog is green. Those all basically mean the same thing. And I would translate that into our new symbolic language using the upside down A. I'd say for every value of X, then I'd say if X is a frog, then X is green, fx arrow gx. No matter what X is, if X is a frog, then X is green. For every value of X, fx arrow gx. And again, you can think of that as going along with a big list of conditionals. Fa arrow ga, if Amherst is a frog, then Amherst is green. If Brittany is a frog, then Brittany is green. If Chicago is a frog, then Chicago is green. Now, all of those are true, even though Amherst and Brittany and Chicago aren't frogs. If you remember the truth table for the arrow, if you have false on the left and you false on the right, you still have a true statement. Let's jump down to the one at the bottom. If Shrek is a frog, then Shrek is green. FS arrow GS, right? That's got false on the left. Now, Shrek is green, so we've got true on the right, but false arrow true is still true, right? The only thing that can make one of these is false is if you have true on the left and false on the right. If you have true on both sides, like FK arrow GK, Kermit is a frog. If Kermit is a frog, then Kermit is green. There you've got true on both sides. That's still true. The only thing, again, that could make this false if you had true on the left and false on the right. Suppose there's some other frog named Leaper. If Leaper is a frog, then Leaper is green. If Leaper is green, then this is okay. You've got true on both sides, and that all of these are still true. But if Leaper is a frog and Leaper isn't green, say Leaper is brown, then we got true on the left and false on the right. That would make it false that all frogs are green. So we understand this with an arrow because we want to say if something is a frog, then it's green, not that everything is a green frog. So we don't use an ampersand here, we use an arrow. So the variable isn't just restricted to frogs, it goes over everything, but for things that aren't frogs, you've got a false on the left, which makes the conditional true. The only thing that can make one of the instances of this conditional false is if you've got true on the left and false on the right. Okay. So anything that's like that, it's about every member of some group, is called a universal affirmative statement. It's saying that something is true about everything. A statement that says something is true about something, but doesn't say it's true about everything, it's true about at least one thing, is called a particular affirmative statement. We translate these with a backwards E applied to a conjunction, that is an and statement, right? So any of these, some politician is honest, some politicians are honest, a few politicians are honest, at least one politician is honest, we translate like this. Backwards EX, PX, and HX. There's at least one value of X where it's both true that X is a politician and it's true that X is honest. So that means there's at least one thing that's both a politician and honest. So in this class, some doesn't mean more than one, it means at least one. Now in English, sometimes some at least suggests that there's more than one, but we're going to interpret some in this class. It just means at least one. All right. We can also think of this as saying something about existence. It says that honest politicians exist. Right? So that's why this is called the existential quantifier. It's not called the existential quantifier because it reads Sartre and likes to think about the anxiety of life and things like that. It's not that kind of existential. It just means it has to do with existence. So we can think of this statement as saying honest politicians exist. If some politician is honest, then honest politicians exist. So that's another way you can interpret the backwards Z as saying something about existence. If we want to say no member of some group has a certain property, we can think of that in two ways. So we want to say no politician is ethical, or no politicians are ethical. Those mean the same thing. Those are called universal negative statements. We can translate that with the upside down A, and then we put a negation after the arrow. For all X, if X is a politician, then X is not ethical, not EX. Or we can translate it with the negation at the very beginning of an existential statement, very beginning of a backwards Z statement. It's not true that there is a value of X where X is a politician and X is ethical. Those two formulations are logically equivalent. We want to say some member of some group doesn't have a property. We can do that with the backwards Z as well, but then we put the negation not before the backwards Z, we put it after the ampersand. So you say some politician is not ethical, or some politicians are not ethical, some politicians are unethical. We say there's at least one value of X, such that X is a politician, X is not ethical. There is an X, PX, and not EX. Or we can also do it with a negation at the beginning of the statement. But altogether, we get what's called the square of opposition. Universal affirmative, all F's or G's, for every value of X, if Fx, then Gx. Universal negative, no F's or G's, for all X, if Fx, then not Gx. Particular affirmative, there is an X, Fx, and Gx. Particular negative, there is an X, Fx, and not Gx. Now, what's funny about this is that the real opposite of all F's or G's is not no F's or G's. Those could both be false. if some are and some aren't. The real opposite of all F's or G's is a particular negative. There are F's that aren't G's. Some F's are not G's. One of those is true, the other one is false, and vice versa. The real opposite of no F's or G's isn't all F's are G's. Again, those can both be false. It's some F's are G's. So universal negative for all x, fx, arrow, gx, in a particular affirmative, there is an x, fx, and gx are really each other's opposites. We're not talking about all members of some group, but just everything. The real opposite of everything is f is something is not f. The real opposite of nothing is f for all x not fx is something is f. There is an x, fx. And what's interesting is that where you put the negations matters. So if I say everything is not f for all x not fx, that's not the same thing as saying it's not true that everything is f, not for all x fx. That just means it's not true, not everything is f. So everything isn't and not everything is are not the same. But for all x not fx does mean the same thing as it's not true there is an x fx. So if you move the negation to the other side of the quantifier and you replace it with the other quantifier, then they are equivalent. So not for all x fx isn't equivalent with for all x not fx, but it is equivalent with there is an x not fx. Similarly, saying it's not true that there is an x fx isn't equivalent with saying there is an x not fx, right? To say that it's not true that something is means nothing is, but to say that sorry, got a little distracted there. To say it's not true that something is means nothing is, but to say that something isn't, there is an x not fx, that means it's not true that everything isn't, right? So they are different. Let's do some example translations. All tigers are mammals means whatever x is for every value. Oh, I should say, when you do this on the computer, a regular A will turn into the upside down A. So I want to say all tigers are mammals for every value of x. If x is a tiger, then x is a mammal. If I'm going to say no tigers golf, I'm saying for every value of x, if x is a tiger, then x does not golf, not tx, not gx. Of course, there is a tiger lowercase t, a name of a specific individual who plays golf, but we're here talking about tigers in general. For all value of x, if x is a tiger, then x does not golf. Some politicians have not driven drunk. Now this is a sum statement, so we're going to do it with the backward z, right? And again, on the computer, we're going to do a forward z that will change into a backward z. There is a value of x, where x is a politician, and it's not true that x is driven drunk. Some golfers love Bjork means there is an x is a golfer. Now we want to say x loves Bjork. How do we do that? So this is LXB. Now lowercase b for Bjork, because Bjork is a specific person. So we're saying there is an x golfs, and x loves Bjork. Right, so we use the variable after the L for the thing that loves Bjork. So it's the golfer, the thing that is an x where x is a golfer that loves Bjork. So nothing is moving is about, you can either say that it's not true that there is an x, that x is moving, or you can also say for everything, it's not moving. Those are equivalent. So for all values of x, x is not moving, or it's not true that there is a value of x where x is moving. But again, where you put that negation matters. If I put the negation on the other side, it's not true that there is an x, It's not true that for all x, mx, that just means not everything is moving, which is different than nothing is moving. So that's not correct. We want the negation over here. You want to say everything is not moving for every value of x, not mx. Something is not moving means there is an x, not mx. And again, the order matters. If we put the negation on the other side, we'd be saying it's not true that there is something that's moving. That means nothing is moving. That's not correct. The negation has to go after the quantifier. So there is an x, x is not moving. If the Mona Lisa is not beautiful, then nothing is beautiful. Mona Lisa is a particular painting. So when we translate the Mona Lisa is not beautiful, we just write not B for being beautiful, lowercase m, because again, the name of a specific painting. If that's true, if it's not true that the Mona Lisa is beautiful, nothing is beautiful for all x, not bx. X is not beautiful. George W. Bush is happy only if no politicians are moral. So George W. Bush is happy is just HG because George is a particular person. George is happy only if, is the arrow, no politicians are moral for all x. If x is a politician, then x is not moral. So that's it for our first lecture. I know I was a little bit nervous and I talked a little bit fast. I apologize for that. But feel free to email me questions. Thank you.